Good afternoon. On this micro-webinar we'll explore the basic concepts that will help you to properly handle risk within your trading system, namely, dependency, mathematical expectation, risk, and the final touches of position sizing. A probability statement is a number between 0 and 1, specifying how probable an outcome is. An independent trial process is a sequence of outcomes where the probability statement is constant, independent from past outcomes. This is called sampling with replacement. An example of this type of process is a coin toss. While a dependent trial process is an outcome sequence in which every outcome is affected by previous outcomes, this is called sampling without replacement. An example of this type of process is blackjack, where the probability of receiving an ace, or any other card number, is dependent on the cards already on the table. Why is it important for us that distinction? If the results of a trading system has dependency, we could improve it by modifying our trade size, dependent on its recent outcomes. For example, increasing or reducing our trade size after a previous gainer, or after a previous loser. If there is no dependency, the trading size should be decided independently of past results. A serial correlation test on our trade history, sometimes called Pearson's R, will tell us if we have a system with dependency. As traders, we must assume that dependency does not exist unless there is overwhelming evidence to the contrary. That is, when trading your system, you will be operating in a context where the result of the next trade is not affected by the outcomes of prior trades. If we act as though there is dependency, when the evidence is not strong, we may just be fooling ourselves and producing more self-inflicted harm than good. A type 1 error is committed when we reject a hypothesis that should be accepted. A type 2 error is committed when we accept a hypothesis that should be rejected. On a trading environment, a type 1 error is to choose not to trade when a system is profitable. A type 2 error is to trade when the system is not profitable. In the first case, we just miss profits, while in the second case we actually lose capital. So, essentially when trading, type 1 errors are much more benign than type 2 errors. Therefore we should reject dependency, unless we are 99.9% sure there is one. So why do we raise this dependency thing? Because many traders believe in it and modify its trading size as if there were dependency, making a costly type 2 error. Also, by assuming non-dependency, we will simplify our position size strategy and make use of interesting statistical properties that will help us understand risk and money management concepts as well. Mathematical expectation, E, is the average amount expected to make, or lose, each bet. Therefore, E is the sum of each trade gain or loss multiplied by its probability of occurrence. On a trading system with multiple trade results, this may be approached by separating gains and losses. Take the mean gain and mean loss, and multiply the mean gain by the probability of gainers, and the mean loss by the probability of losing, which is 1 minus the probability of gainers. Example 1. Let's find E on a game with 50% chance of winning $2 and a 50% chance of losing $1. In this case, E is equal to 0.5 multiplied by 2, plus 0.5 multiplied by minus 1, which is 1 plus minus 0.5, therefore, E is equal to 0.5. As a result, on this system we expect an average profit of $0.50 on each trade. Example 2. Let's find E, for betting on one number, with 35 to 1 payout, on an American roulette. In this case P equals 1 over 38, so E is equal to 1 over 38 multiplied by 35, plus 37 over 38 multiplied by minus 1, which is roughly equal to 0.0263, by 35 plus 0.974 by minus 1. And that is equal to 0.921 plus minus 0.974. Therefore, the roulette game has a mathematical expectation of minus 0.053. So, in this case we expect to lose on average 5 cents per dollar bet. Therefore, no money management makes this system profitable in the long run. Finally, let's see graphically how position sizing affects profits and drawdown. We will use a single normalized history of 100 trades. We will use a starting capital of $1,000 in all cases. On this slide, we present a trading history, using a fixed bet size of $10 per trade. We observe that the final trading balance is about $1,118. Its maximum peak is about $1,150, and its max drawdown is roughly 4.3%. On the following slide we use a fractional bet size of 1% of the running capital. The result is quite similar to the previous one. The final trading balance is about $1,115, its maximum peak about $1,160, and its max drawdown is roughly 6%. On this one we use a fractional bet size of 5% of the running capital. The result shows a jump in profitability, as expected. The final trading balance is about $1,600, its maximum peak near $1,900, but we observe that its max drawdown jumped to 23.7%. Now, we have increased bet size to 10% of the running capital. This trade size raises profitability again. The final trading balance is about $2,100, and its maximum peak near $3,400, but the observed max drawdown goes to 50%. On this slide, we increase bet size to 20% of the running capital, but this trade size does not raise profitability substantially. With a final trading balance of about $2,200, its maximum peak goes to more than $6,000, and its observed max drawdown jumps to 71%. Finally, on the slide we use a bet size that's 30% of the running capital. This trade size not only does not raise profitability, but it heavily reduces it, with a final trading balance of about $1,200. Its maximum peak goes close to $8,000, and worse, its observed max drawdown goes to 78%. So we may conclude the following: position size matters. It is the tool that allows us to reach your objectives. As position size increases, so does drawdown. After some fractional value, position size not only increases drawdown but decreases profits. You already know what expectancy is, but the beauty of this number is that, together with the average number of trades, it tells you the R multiple your system delivers in a time interval. We know from a previous slide that E, the mathematical expectation, is the average profit per dollar risked on each trade. Therefore, the unit profit after N trades is equal to E multiplied by N. If the system delivers a mean of 6 daily trades, then the daily dollar profit is 6E, and the mean monthly profit will be 120E. Therefore, knowing the expectancy of your system allows you to compute how much risk do you need to reach your monthly objectives. As an objectives calculation example, let's use the game of case 1, and assume that this system delivers a mean of 6 trades per day. We know that this game's E is $0.50, so its daily returns will be $3 per dollar risked, or 3R, and its monthly return would be 60R. If your objective is to reach $3,000 monthly, what should be your risk? Your risk, R, equals $3,000 divided by 60, or $50. Now you know, for instance, that you could achieve $6,000 monthly by doubling your risk to $100 per trade, and $12,000 monthly if you can raise your risk per trade to $200. You have converted a system into a powerful money-making machine, but with a risk-controlled attitude. But we know that if we bet too strongly, it goes against our self-interest. So, how do we know how much risk we should accept? As traders we know, drawdowns are to be expected. As we saw previously, drawdowns are related to position size. The higher the size, the higher the drawdowns. So how do we know how much drawdown we should expect from a determined position sizing strategy? We can approximate this value by computing how much a losing streak might cost us. If we wanted to be on the safe side, we should use a higher than 8 streak, possibly 15, if your system delivers less than 40% gainers. Example. A trader with a $10,000 account wants to be protected against a drop of 10 consecutive losers, and with a maximum drawdown below 20%. Max drawdown equals $10,000 multiplied by 0.2, which is equal to $2,000. Max risk equals max drawdown divided by the end streak we want to be protected against. Therefore, max risk equals $2,000 divided by 10, which is equal to $200. If we want a constant 20% protection, as the account grows and shrinks, then we should move to percent calculation. To achieve this, we equate max risk as a percentage of the initial capital. Therefore, a risk of $200 is 2% of the running capital. That protects us much better, because position size decreases as the running capital decreases. Now, the final piece of the puzzle is how to calculate the lot size to guarantee a constant dollar risk. Let's do it using an example. Consider the risk of a micro lot of the EUR/USD pair in the following short entry. We know that the size of a micro lot is 1,000 units. Our trade direction is to short the pair. Our entry point is 1.19344 and our stop loss 1.19621, so the distance from entry to stop loss is 0.00277, and the dollar risk for one micro lot will be 0.00277 multiplied by 1,000 equals $2.77. Thus, if out max risk is $200, then our position size should be $200 divided by $2.77, which is 72 micro lots. Using this concept, we can standardize our position size according to the individual risk. For instance, if the unit risk in the previous example were $5 instead, then the position size would be 200 divided by 5, which is 40 micro lots. We would enter a position with a standard and controlled risk, independent of its distance from entry to stop. Next webinar will be dedicated to the basics of the Elliott wave theory. Thank you for your attention.